Closing out the week is Advanced Strain Solutions for Biomedical Testing. Thanks so much for joining us. I'm Veronica Costa, your host. For this session will be covered by Dan Raynor, Instron's Product Manager for Strain Measurement. Dan is going to discuss many of the common challenges in biomedical testing applications that can necessitate the use of more advanced solutions with strain measurement. This will also include an overview of digital image correlation software, or what we call DIC, for generating full field strain and displacement maps for materials and component testing. Dan has been part of the Instron team for over 16 years and has experience supporting our electromechanical low force and high force applications, as well as static hydraulic and dynamic. You may have had a chance to work with Dan personally. He's spent the majority of his career partnering directly with our customers on site and back at our headquarters in Instron's applications lab to determine the best solutions for your specific testing needs. Dan's joined by Landon Goldfarb. If you had a chance to participate in the PPE testing session on Monday afternoon or the testing optimization session on Tuesday afternoon, you've met Landon. Both of these sessions, by the way, are up on our YouTube channel. Landon is one of our senior applications engineers and has a great deal of experience working directly with our biomedical customers around the globe. Landon will be handling a couple of the slides and also assisting Dan with questions. So feel free to add any of your questions into the chat box on the panel as we go along. And one last thing I did want to mention before we begin, for those of you who have attended some of the other sessions, you're already aware of this. But for those of you that are interested in receiving the single-use code for free access to the Essentials of Biomedical Testing e-learning course, this is just a quick reminder that you'll want to complete the post-event survey that will display immediately following the session. And I'll be sure to remind you about that again at the end. So with that said, I'm going to turn things over to Dan.
Thanks very much, Veronica. So we'll get started with our presentation. I assume everyone can see it. So this is the Advanced Strain Solutions for Biomedical Testing. And to put a face to the voice, I'm Dan Raynor, and that's Landon Goldfarb, application engineer extraordinaire. A couple of the topics that we're going to talk about today. So we're going to do a brief overview of what is strain. Looks like a lot of you do have some experience with strain measurement. Talk about some extensometer types. So of course, there's all different applications out there, and we have a lot of different extensometers to work with them. We're going to look for some of the solutions for delicate biomaterials, as well as a Nitinol specific application. And then finally, we'll go over some digital image correlation that a lot of people find useful for rigid materials, as well as soft tissue, working with FEA modeling. And then finally, show you the DIC replay software that Instron offers. So we certainly want to talk about the different applications. There's a number of test standards that require extensometry, but a lot of our customers use extensometry just for more information about their material or their product. So this way they can fully characterize it. We certainly understand that liability can be quite high when products are used on or in the human body. So that's one of the major driving forces. So what is strain measurement? Many of you are aware that strain is a measure of the specimen's elongation while under load. It can be expressed as a constant of unit, length per unit length, so millimeters per millimeter. It could also be shown as a percentage of the initial gauge length. In many cases, or in some cases, strain can be measured along more than one axis. So it could be axial strain or transverse strain. There's also diametral for say a round specimen in compression to see how much the diameter changes. So L naught in this image would be the initial gauge length, and then you have some delta L that's added onto the length as it's pulled. In this example, it's under tension. So for types of extensometers, many of the traditional extensometers, we have clip-ons, so they attach physically to the specimen for static testing, for dynamic fatigue testing, biaxial clip-ons for measuring axial and transverse at the same time, also Poisson's ratio, and COD gauge, which is a specific application for fracture mechanics. We have long travel contacting extensometers. So the XL extensometer is typically for elastomers. Accuracy is not as critical, but the amount of travel is important. And then of course we have the Auto X750. This is a fully automatic extensometer with excellent accuracy down to 1 micron, as well as 750 millimeters of travel. So we can kind of cover the whole range of materials. It's fully automatic in the sense that you can set the gauge length and the arms opening and closing all automatically. And we can also add transverse strain measurement to this as well. Then of course we have non-contacting. So the SVE or AVE2, which we're going to talk a little bit more about. And it also works with DIC replay. So the digital image correlation software that can utilize the existing hardware. But the most important thing is that extensometers measure strain directly from the specimen or as close as possible, as opposed to measuring from the crosshead or the grips. So traditional extensometry, as you mentioned, it's some form of contacting the specimen. Typically, it'll clip onto the specimen and self-support its own weight. We use spring clips or elastic bands to hold it on there. And there are pretty sharp knife edges so that it can accurately track the deformation between 2 points without slipping on the specimen during the test. Exactly. So the other important thing to remember, though, is that this clip-on extensometer and the sharp knife edges, thin specimens that are not strong enough to support the weight or might get cut by those knife edges need a different solution. And so it's by measuring between the 2 points on the specimen, it's not affected by the jaws moving in the wedge grips. So in this image, these spaces are actually designed to self-tighten. So as the higher load is applied to the specimen, the faces will move and get tighter on the specimen. That movement would not be measured by the clip-on extensometer and incorrectly measured as strain. So that's one of the benefits of using a clip-on. So strain measurement and compression can be a little different. It's often required in the sense that you want to know exactly what is happening at the specimen. The readings from the system's actuator or the moving crosshead may not be acceptable because they include several different factors that affect compliance of the load string. So it could be the load frame itself, the drive system, the load cell is technically a spring, as well as adapters and platens. So strain measurement of bone also presents challenges. In this image, you can see that the specimen is submerged in water, and we've got 2 little arms coming out to measure the strain between. So a full-size bone or a larger specimen could support a clip-on extensometer, but for smaller specimens or ones that you can typically they'll measure the strain off of the fixture, and that's about as close as you can get to the specimen. So, like we asked you, kind of what industries all of you are typically involved with. We've got solutions and applications for many of our different customers between its biomaterials or implants, consumables, and dentistry. And they all have their own idiosyncrasies. So getting into delicate biomaterials, we typically see soft tissue. It can't really support the weight of a clip-on extensometer. Even the lightweight versions are sometimes too heavy, or again, the knife edges can affect the material. And the strain measurement, by measuring the strain of the specimen, it eliminates the effects of extrusion from the grip faces. So even if we use pneumatic side-acting grips, some of the material might stretch out of the face during the test, and which would affect the initial gauge length reading, because you're kind of artificially increasing the length of the specimen without extensometry. So that brings us to non-contacting extensometry. So there's certain benefits over traditional contacting specifically for biomaterials. There's no influence on the test specimen itself other than placing marks on the specimen. You don't have to worry about knife edges slipping on the specimen, if you could even fit them on there to begin with. Of course, sometimes there's effects of, in a very fast test or a cyclic test, there's the inertia of the extensometer itself hanging on the specimen that can cause issues. And the non-contacting extensometry can be used in fluid baths or temperature chambers. So Instron has an advanced video extensometer, or we call it the AVE second generation, AVE2. It's non-contacting, can measure axial and transverse strain in real time. There's several patents have been awarded, and there's actually several more that are pending. 490 Hertz image capture rate. There's multiple field of views, so it's a very flexible device, going from, a very accurate smaller field of view to a still very accurate larger field of view for elastomers and higher materials that'll elongate more. There's also the ability for dynamic strain measurement and control capability for a cyclic fatigue test. It's fully integrated with an Instron test system, so all the data is synchronized with the load and displacement. And you can save images during the test for use with the DIC replay software. So one of the trickiest parts is specimen marking for different materials. So some materials are affected by different inks or solvents. Other materials are slimy and wet, and it's very difficult to get a mark to stay on there, whether it's from a marker or a sticker. But for ambient testing of soft, compliant, and moist tissue specimens, we can use paper dots or even graphite powder. For in vivo testing of soft, compliant, and moist tissue specimens, we use black magic marker, super glue, or a mixture of graphite powder and super glue. And again, for in vivo testing of rigid or flat materials, the magic marker dots or lines work well, and also water-resistant paint. And then we've got for in vivo testing of rigid round materials, so thin wires typically, we can use adhesive putty to create a dot or a round sphere around the specimen or flags. This image shows a hydrogel specimen that's actually being held between pieces of paper so it doesn't slip on the little small spring-loaded grips. These are 5-Newton grips, and we've got 2 white dots that the video extensometer would be tracking. So that brings us to digital image correlation. DIC, which we didn't invent, but it's an optical technique to compare images of a specimen surface during a test. And what it does, the images are taken during the test, but the DIC is calculated post-test, and it generates a full field strain and displacement map. And from that, you can get all sorts of information. So the idea is that it provides a measure of strain at every point on the specimen, as opposed to just between 2 dots. And we'll get more into the DIC replay software in a little bit. Brings us to our BioPulse bath, as we mentioned in vivo testing. So it's for customers testing kind of the physiological conditions. So whether it's in a human body, there's a closed loop heater control for accurate temperature adjustment. It's set from the factory at 37 degrees Celsius. It's suitable for single and dual column systems and most of our legacy systems. It is limited to 250 newtons of force due to the pneumatic grips that are part of the setup. It can be used with an SVE2 or an AVE2. There is a pneumatic lifting mechanism, so it allows you to replace the specimen without having to drain the bath. You simply raise and lower the bath around the test space. And if you need to go to higher temperatures or even much lower temperatures, we have temperature chambers, which this image shows the video extensometer mounted on the face, looking through the optical quality glass. So we have temperature ranges from -150 Celsius up to 600 degrees Celsius. Of course, our chambers can be tuned or optimized for 37 degrees Celsius if you only need body temperature. And they're very common to be used with nitinol wire testing, since the extensometry is required for most of the nitinol tests. Which does bring us to the nitinol. And Landon, can I ask you to go through these next couple of slides?
Yeah, absolutely, Dan. Thank you. So nitinol is a really commonly used material in the biomedical industry for two reasons. One is its shape memory, and two is its super elastic properties. So super elasticity makes it ideal to be used in stents that would be used during an angioplasty procedure. It's able to compress while it's being placed and then expand to its original size once deposited in the artery. Nitinol shape memory makes it a really novel solution in orthodontics. For instance, if you were to use it for braces, it actually will heat up once it's placed in the mouth, and then that action will actually cause it to try and revert to a straighter shape, and that actual action is what's stressing the teeth into moving into the right position. In addition to the component and subcomponent testing needed for these products, the raw material also needs to undergo rigorous testing to confirm its properties. ASTM F2516 is the main standard that evaluates the tensile properties of nitinol and requires the use of an extensometer for any wire greater than 0.2 millimeters in diameter. So we actually have performed a pretty extensive extensometry study in conjunction with Fort Wayne Metals, who's a major manufacturer of nitinol, and we showed that for thicker specimens, clip-on devices, AutoX, and AV all produce statistically similar results. Obviously, once you get to thinner specimens that still need an extensometer, the non-contacting solution is a better option. So here we have a pretty typical test stress strain curve that you would get from F2516 that was actually captured using an AutoX. So the test curve is really unique, which highlights the super elasticity of the material. As a stress is applied, the phase change in the material is actually induced from austenite to martensite. At a turnaround of 6% strain is required, considering 8% is really the absolute limit for when you would actually have plastic deformation. The system uses real-time extensometer data to detect and initiate the turnaround. When the material is unloaded, the phase change actually reverses, recovering nearly all of the elastic deformation. You can see the residual elongation is just a small amount of permanent deformation after the unloading process. Once the hysteresis is performed, the material is generally always pulled to failure, identifying the tensile strength and uniform elongation. And with that, I will hand it back to you, Dan.
Great, thanks very much, Landon. So that's going to bring us to the DIC portion of this. So we've got a little video here for you. Let's see how this works. So this is, it's actually a composite specimen, but there's a hole in the middle. And so the digital image correlation software is able to plot the full field strain map around that hole. And you'll see that it's pretty homogeneous in the beginning. All of the pink area you're seeing is been selected for the strain map calculation. And so it's all straining pretty much at the same rate. That's why it's mostly the same color. But now we can see on the left and right sides of that hole in the center is where we're starting to see more strain being induced. And as it goes along, you'll see that increase. And we'll skip ahead a little bit. So you can see all of the strain is pretty much focused on the edges of that hole right now. And this is what you'd be able to see with some, odd shaped component where you couldn't physically put an extensometer on the edges of that hole. You'd probably see bonded strain gauges. And if it is, a piece of bone or some other orthopedic device, it'd probably be pretty tricky to do as well, consistently. So with this, we can speckle the material and run the test and let the software do the work. And it'll break just as it gets to the end of this video, and you'll see all of the strain at the break area, and everything else will be back to in its elastic form. So for those that are not familiar with it, what is digital image correlation? So it's an optical analysis tool used to visualize strain. Traditional extensometers only give a point-to-point measurement. It helps eliminate errors of average strain measurements, which is when you're measuring between 2 points, you could be covering 50 millimeters, let's say, of the whole specimen. And you don't exactly know where the strain is occurring between those 50 millimeters. It's basically averaged throughout the 50 millimeters. So this is especially important for specimens where heterogeneity is significant. So you really want to see those local strains. So from these images, you can see these are 4 images of the same compression test. We've got an arrow here showing kind of a strain concentration at the top. And then as we get to the last image, we could see it start to buckle, and we can see some more strain concentrations, which you can't necessarily see with the naked eye, and you certainly couldn't put a clip-on extensometer there. Or you'd have to know where it was going to happen before the test as well. And so why is DSE used? So again, it's used to visualize non-uniform strains in materials that need to be fully characterized. So the full field strain map, often used to verify, whether it's a new finite element model. And this is common where the no perfect model exists and you need empirical data to compare to your model. It's also useful to detect flaws in components or materials. So we can see high strain concentrations that could indicate a presence of a crack or a void. And that's what we see here in this image. So if we know all the strain is occurring at this line, there's a very good chance there's actually a crack there. And in addition to axial strain, you can see many other types, whether it's different strains, so transverse or shear, as well as displacements, Poisson's ratio, and of course normal strains as well. So how does it work? We've got essentially a reference subset of dots. So you have a non-uniform pattern is applied to the specimen, whether it's sprayed on or some other means, or even sometimes the surface pattern of the specimen itself could be used. So DSE works by taking a series of consecutive images of these patterns during the test. And then they're analyzed after the test by comparing one image to the previous one, or sometimes several previous. And so the deformation of the pattern is calculated. So I think a good example is we start off with these 2 images. You can see the one in the foreground has been stretched a little further. So we get a displacement map, and we can see that more displacement is occurring in the middle. And then that's where our strain map goes, where we now could see this heat map of where more of the strain has occurred. So a good example is also a fracture fixation plate. So the idea is that it is used to immobilize, say, a broken ankle in this image, as you can see through an X-ray. So we've got the metal plate here and several screws going into the bones. So there's several different forces acting on these as well, though. So there's tension, compression, flexure, and certainly fatigue. So every step that this person would take could be applying different forces to it. So it's really hard to run one simulation or, really get, to be able to run tensile tests and determine if it's designed well or not. So it's a combination of loading simulations and physical testing is performed. So there has been, over the last few years, there's some trends in the ASTM orthopedics testing. There was a new standard, the F3161, which provides guidelines for testing knee femoral implants with strain gauges to correlate the results with finite element analysis. So there's several ASTM working groups on defining the standard to provide the best practices for using DIC as a validated modeling and simulation data. Of course, the challenge is to correlate that loading data with physical testing data. And so Instron actually did a study. We used the DIC replay software to get a strain map of basically a representative specimen. This was an aluminum specimen that was machined to have several holes in it and looks somewhat like you might find in the specimens for the orthopedics. And then we compared it to the FDA stress map from SolidWorks in this case. So you can see it pretty much agrees in many places. There are some slight differences because this is looking at strain and this one's looking at stress, but there's also, this isn't accounting necessarily for any variations in surface finish or machining. So as I mentioned, the pros and cons in this case, the simulation offers full field stress map, can handle complex geometries, and it's certainly cost effective as opposed to running many physical tests. But it does ignore machining and also boundary conditions can be subjective. Then you have the physical testing pros, is that it's real world failure analysis. It can account for machining and any other variables. But the cons is that the stress calculations are generalized for complex geometries, and it's also time intensive. So that brings us to the Instron DIC replay software, which I'm not sure if some of you may have seen this. We've had it out for 6-7 years now or more, 8. So the idea here is that it gives you a nice little kind of a wizard to walk you through from images to actual getting data from a strain map. And I'll probably reiterate some things that I've already said, but the idea is that the AVE2 will capture the images. The test is run on an Instron frame, so the data from the frame is automatically synchronized. The images are analyzed on the same PC to create the strain map. The 2D strain map gives data for specimens that can't be measured easily, like I mentioned. Of course, you can add virtual extensometers and strain gauges, and they can be placed on the specimen pretty much anywhere for material testing specific results. The data can then be exported to Excel for further analysis, and we can export videos as well. So it's the intent there is that, again, we didn't invent DIC, but we'd like to think by integrating it, we made it faster and easier to conduct your testing. We'll see if this works. So we've got a video. I'm going to play it. So as you can see, this is taken images from a specimen test, and now we've imported those. We've selected the area of interest, which we can do with a rectangle, and actually there's a newer feature which will automatically select the area for you that's been speckled. And then we press play, and it starts calculating the strain map. In this case, it's axial strain is what we're viewing. And you can see where it was pretty much homogeneous, but now the strain started kind of going towards the middle, and that's where it eventually failed. That's where the highest strain is. And here we're applying a virtual extensometer, and then we'll also add a strain gauge. And then we can go back in and actually tweak the absolute value of them, so we can be right at 50 millimeters for the virtual extensometer, and then 5 by 5 for the strain gauge. And that's essentially, within a few minutes, you have that strain map, which we save the map itself for future analysis. But now we can also plot the values from these virtual strain gauges and strain and extensometer versus the data from our Blue Hill Universal test of load and stress and displacement. And then we can export everything as a CSV, and we can also export a video of the strain map itself. And if anyone has any questions, we'd be happy to answer them now. I think we had a few questions from before the presentation when some of you were registering. So I'd say one of the previous questions was, is this DIC software able to deal with CT scan data for segmentation of sliced images? That's a really interesting application, but at the moment our DIC software is only able to take images from our video extensometer. Again, our intent is to basically make it easier by integrating it with the test system. So it's not, if we need to do something a little more complicated or more powerful than that, we've partnered with a company called LaVision, and they can pretty much do anything we've ever needed to do. So we could certainly, I would recommend reaching out to LaVision, who creates DIC equipment and software for anything more complicated. I know some people were interested in more about soft tissue strain tests. There's again, we kind of brushed upon the non-contacting, which is certainly the way to go for soft tissue. Gripping it can be difficult enough sometimes. We have a lot of options for that as well. But then measuring strain on it is, again, once you figure out a marking technique that works, it's pretty easy for the video extensometer to track that. But there's a lot of information there that we could potentially help with. I know we've done several webinars recently on just kind of general tricks for materials testing, but also things to watch out for that can affect your materials testing. And there's a large diagram that kind of covers whether it's gripping or measurement, data rate, all sorts of things. So I guess I would encourage you to go to the Instron website to find the previous webinars that could offer a lot of input. As well as someone asked how to ensure your testing is accurate for mechanical testing of soft but tough biomaterials. That along those same lines can be rather tricky. I'm guessing most of the issue is gripping technique, because how do you hold something tight enough without damaging it when it's slippery? So yeah, if you want to reach out to us individually, that could certainly, we'd certainly be happy to help. And again, there's probably some information in some of the previous webinars we've done on the Instron website. Looks like Landon, did you have a couple questions that you'd like to take?
Sure. So a couple questions came in. So the first one being, can DIC be used for an indentation test? So for an indentation test, that really is a three-dimensional deformation that needs to be tracked. So DIC as it stands is a 2D system, so it really is looking at a flat surface. So as Dan mentioned earlier, we do partner with LaVision to do more advanced 3D DIC systems, but that would use different hardware. But there is capability to do that within the confines of using a Instron tensile tester. So there is the possibility to do that, but the DIC replay that we discussed today is purely a 2D solution. We had another question about the sample size that the AV2 can handle and the amount of extension it can track. So the AV2 has different lens options. So there's 4 different lenses that are pretty easily swapped in and out. So the lens each will have a different field of view. So we have all the way down to a 35mm focal length lens, which is for really small amounts of strain, and that's also the most accurate. As you move from smaller to larger fields of view, your accuracy will go down. If you were to go all the way to the 6mm focal length, which is actually the largest field of view, you have almost 600 millimeters of travel, and depending on the specimen gauge length, the strain can go up to 1,000, 1,500%. So there's a very wide range of specimen sizes and extensions that can be tracked with the AVE.
So I don't know if anyone has any additional questions. Otherwise.
All right. Well, thank you very much, Dan and Landon, for hosting the session and for the questions. And that's going to do it for today. We just have a few quick notes to wrap things up. The recording for this session will be on YouTube in just a short while. And each of you will also receive an email with a link to the recording. And we'll also have all the other sessions that we had going on this week recorded and up on YouTube as well. So just another reminder about receiving that single-use access code for free access to the Essentials of Biomedical Testing e-learning course. In just a moment, when the session ends, you'll see a survey pop up. So if you could just answer those questions, there'll be one that's related to the course. So you just need to select yes, and then we'll be sending that over to you. So with that said, we just want to thank Dan and Landon again for a great presentation. And thanks to everyone for your participation. It's been a great week, packed with lots of relevant information, and we really appreciate your time. Well, have a great day and stay healthy, everyone. Thank you.